Let me announce our first keynote lecture with the title Lipschitz Global Optimization and Machine Learning, Helping Each Other to Solve Complex Problems. Our keynote speaker is Professor Konstantin Barkalov from Nizhny Novgorod State Federal University, Nizhny Novgorod City, Russia. You are welcome, Professor.
Thank you. Thank you very much. Now I try to share my screen.
Yes, we can see your screen.
But now I try to start presentation in the full screen mode. Do you see it? In the
Yes,
full screen?
perfect.
Okay. Let's start. My name is Konstantin Barkalov. I'm from Nizhny Novgorod State University. This first slide, you may see a beautiful view of our city on the banks of two great Russian rivers, Oka and Volga. Well, and in this talk with my co-author, my PhD student, Marina Usova, I want to consider some Lipschitz global optimization methods that we develop in our university and how we can apply it to help machine learning methods and how machine learning can help to global optimization methods in some complex problems. Here we see the content of my talk. First, we consider very important problem of hyperparameters tuning and how we can apply Lipschitz global optimization here. And I say a few words about parallel methods of global optimization. We discuss about the numerical results. And the second part of my talk devoted to multi-objective optimization problems, how we can solve it and how we can use machine learning techniques to accelerate the search. Let's start. Hyperparameters tuning problem is very often arise in practice. Practitioner or researcher who apply some machine learning method knows very well that the efficiency of this method, some efficiency criteria strongly depends on the hyperparameters. And this practitioner can select these hyperparameters using the experience and evaluate the best combination. But the very simple idea is to use some solver, some meta optimizer that helps us to select the best combination of hyperparameters that corresponds to the best, in some sense, the score, the efficiency criterion. If we discuss about machine learning methods, these efficiency criteria can be the loss function. We want to minimize the loss function on a certain data set according to the concrete values of hyperparameters. There are a lot of methods that we can apply to do it. The simple, or maybe the simplest method is a uniform grid search. We can select all the combinations of the values of hyperparameters, evaluate their criterion the matrix at every point and select the best solution. Of course, this grid is dense, and this method can be applied only for problems with just a few hyperparameters. The random grid can be built using a random search. In this case, this method can be applied for problems with larger dimensionality, but it doesn't guarantee that we find a good solution for a small number of trials. More powerful methods are Bayesian optimization. This technique allows us to build a grid, the points of which concentrated only near the global solution, or nature-inspired algorithms. So a lot of techniques that we can use to tune these hyperparameters for machine learning methods. And these techniques already implemented in many open source frameworks. Here I mentioned just a few of them: HyperOpt, Aptuna, Scikit Optimize, and a lot of frameworks, a lot of other frameworks. But from the point of view of, from the mathematical point of view, hyperparameter tuning problem can be formulated as a global optimization problem. We want to find the global minimizer y star of some real valued function phi of y that defined on some hyperinterval. Usually this hyperinterval is given in the form of hyperparallelepiped D. And the key feature of this problem is that we don't know the analytical formula of a function. The function is represented in the form of a black box. We can compute the function output, the function value phi of y, according to some input. This function can be multi-extreme. In some cases, in some problems, there are a lot of efficiency criterions. In this case, we have multi-objective optimization problem. And for these type of problems, it's not enough to find only one solution. We should find a set of efficient solutions, so-called Pareto set or Pareto front. All of the methods that we can apply can be divided into two large groups of the methods: deterministic algorithms and meta-heuristic algorithms. On this slide, I list some features of the algorithms of these two groups. Deterministic algorithms give us the same result when we run it several times. Usually, it shows good results for small-scale problems when the dimensionality is not very large. And unfortunately, these algorithms practically are not applicable for large-scale problems. Well, once again, we consider the problems with a black box function, where we can only evaluate the function values. And meta-heuristic algorithms that are one way or another based on a random search concept gives us a different result when restarting. And they require several runs to find a good solution. But at the same time, it shows rather good result in large-scale problems for large dimensionality. And also, these methods contain parameters that greatly influence the resultant solution. But all of the methods, both deterministic, both meta-heuristic algorithms, to find a global solution, build a grid in a space of parameters. And this grid can be dense as in random search method, but to build an efficient method, we should generate a grid that is dense only near to the global optimum, and is sparse far from it. One of the assumptions that allows us to construct such efficient methods is as follows. The limited change of the function argument, delta y, produces a limited change of the function values. Mathematical model of this assumption is a Lipschitz condition that tells us that difference of the objective function values bounded with the difference of the arguments multiply some constant L that called Lipschitz constant. Usually this constant is unknown and should be estimated during the search. Using this supposition, we can build a so-called supporting function or minorant using just a few search trial points. And we can use this minorant to predict the behavior of the function and put the next trial point at the minimum point of this minorant. There are a lot of researchers who investigate the Lipschitz optimization methods. Again, here I mention just a few of them. In Nizhny Novgorod State University, under supervision by Professor Roman Strongen, we developed a rather efficient approach for solving such type of problems. But again, in any case, any methods for solving this type of problems, one way or another, exploits the idea of adaptation, one-dimensional method to multidimensional case. These ways how to adapt one-dimensional algorithms usually suppose their subdivision of search space onto hypercubes or simplexes, and this approach proposed by Sergeyev and Kwas of diagonal partition methods. Here the behavior of the function is in hypercube is predicted by analyzing the one-dimensional function or on this main diagonal of hypercube. Simplician partition methods proposed by Zhilinskas, where we where the authors evaluates the behavior of the function in the simplexes. And so in our study, in our approach, we use a completely different idea to reduce multidimensional problem to univariate one. We used an approach based on the Peano space filling curves. This type of curve maps the unit interval onto the n-dimensional domain. Using this curve, y of x, we can take the point x from the unit interval, compute its multi-dimensional image, y of x, in a such domain, and evaluate the function value at this point, 5y. After that, we can interpret it as the value of a univariate function, 5y of x. That's why we can consider the problem, the minimization of multidimensional function 5y as a univariate problem for finding the global minimum of the reduced function 5y of x over the standard interval. Of course, the Peano curve is a limit object, and for practical applications, we should use some approximation to Peano curve. Numerical methods for building such approximation, we call it evolvens, are considered in the books written by Strongen and Sergeyev. This method allows us to build approximation of with a predefined accuracy for predefined dimensionality. And the key feature of this approach is that if original function 5y satisfies Lipschitz condition with some constant L, then the univariate function 5y of x will satisfy Hölder condition. Of course, Hölder condition is not so good as a Lipschitz condition according to this power 1 over n, but anyway, the boundedness of the difference of objective function of the objective function value holds. And as far as we consider any problem as a univariate problem, we can formulate the core global search algorithm. The main rules presented here on this slide. As a search trial, we consider the calculation of a reduced function value, 5y of x, at some point xi. First two trials are carried out at boundary points, x0 and x1. Then, for each interval, we compute the value, we call it characteristic of this interval. We find the best interval with the maximum characteristic and carry out a new trial at the internal point of this best interval. So we can say that this method, the global search algorithm, belongs to the divide the best methods. And if this best interval becomes significantly small, the method stops. Concrete formulas for computing characteristics of the interval, that includes also the formula for adaptive estimation of Lipschitz constant presented here on this slide. And also here we see the formula for computing the point of the next trial. Complete theory of convergence of global search algorithm is presented in a book written by Strongen and Sergeyev. Here I mention just the main result, the convergence condition, can be formulated in the form of this theorem. If the objective function 5y satisfies the Lipschitz condition with some constant L, And if at some step of the search process this inequality holds, where R is a parameter of the method, mu is adaptive estimation of the true Lipschitz constant, and n is a dimensionality of the problem, then any limit point of a sequence of trials generated by the algorithm is a global minimizer. And vice versa, any global minimizer of the function is a limit point of a sequence of a trial. But the key feature is that this sequence of trials, y of k, is not everywhere dense. On this slide, you may see two examples, level lines of multi-extremal functions and trial points. It's clear to see that these trials, the points of the trials, concentrated only at the vicinity of a global optimum. And the number of trials required to solve these problems with their accuracy 10 power minus 2 presented here. It's here we see just one example, but we test our methods on a series of problems generated by so-called GKLS generator. This generator allows us to build multidimensional test functions with known properties, with known local and global minimum. This generator you may find here. And we generate two classes of problems, more simple and more hard problems from the point of view of global optimization methods. These problems have 10 local minimums, the same value of global minimum and the global minimizer, but it differs in a radius of the attraction region of the global minimizer and the distance from the global minimizer, this one, to the vertex of the paraboloid. We compare seven methods with our global search algorithms. These methods we take from SciPy and NLOP libraries, and we compare GSA with deterministic algorithms like direct and direct L and nature-inspired algorithms. On this slide, you may see the performance profile or operating characteristics of the methods. These curves reflects the relation between the number of function evaluations and the number of solved problem. These are number of function evaluations. The higher this curve lies, the better. And you may see that the curve that corresponds to the global search algorithm lies significantly higher, and our method works rather well. But these are the simple problems, and situation differs when the problems are hard. In this case, the most part of the methods are failed to solve 100% problems. I failed to solve. Only deterministic methods can do it, but our method outperforms well-known direct algorithms. Here we compare their serial sequential algorithms, sequential methods. Just a few words about parallelization. Let me remind you that we consider all of the methods, all of the problems as a univariate using dimensionality reduction based on Peano curves. That's why the idea to parallelize is rather simple. Let's select not only one best interval, but let's sort all of the search intervals in descending order according to their characteristics and select P intervals with the largest characteristics. And after that, perform P trials in parallel at internal point of this best interval. If at least one of these best intervals becomes small, the method stops. This general idea very well corresponds to the master working model in parallel programming. The master process computes the coordinates of points of a new trial. The master processes all their accumulated search information. After that, when the master computes these coordinates, it distributes it among the working processors. Each worker carries out one trial, so it computes the function value, and the results of all trials are transferred to master. I don't want to go into details here. I show just one simple example of the same problem that I already showed you. The serial algorithm requires 260 iterations to solve it. That corresponds to the same number of trials. The parallel algorithm requires the larger number of trials, but this larger number of trials carried out at the smaller number of iterations. These additional trials indicated here as pluses. And the speed up of by iterations for these problems for 4 parallel processes is approximately 3.4. Later I show you another examples. All of these methods, all of these algorithms are implemented in IOPT framework. IOPT means Intellectual Optimization Framework. This is open source framework. You can find it here by this link. And this framework oriented for tuning the parameters for mathematical models of complex objects and process, especially machine learning methods and discrete optimization methods. It integrates with external library and external frameworks. The process can be visualized. And now I want to show you just, again, a few examples how we can use this framework to tune machine learning methods. First example related with tuning of a support vector machine. This method allows us to build a separating hyperplane or separating surface and used in classification and regression problems. This method has two parameters, regularization coefficient and the kernel coefficient. We use open dataset, breast cancer dataset, and solve classification problem. This graph reflects the objective function. As objective function, we use F1 score, and you can see that the objective function is multi-extremal, and with the default hyperparameters, the value of this F1 score is 0.87. If we apply the method from Scikit optimize for tuning the parameters, we can get more high value of F1 score, 0.9. But if we apply the methods from iOpt, we can get the value 0.97. And this table reflects the effect of parallelization. Here we see the number of processors and the time required to solve the problem. Of course, the speed up is not linear, but it's rather good for 80 parallel processes. Of course, we compare our methods not for one problem. We use a lot of data sets, and we compare iOpt with different frameworks, different methods, Aptuna, HyperOpt, different methods from these frameworks. This table reflects the results that we get for tuning parameters for support vector machine. And the bold font here corresponds to the best average value. And the red font corresponds to the best value in the worst case. And as you see, our framework gives the result that so in the most cases, best both in the worst case and is best on average. As far as these methods are meta-heuristics, we run it 10 times and average the results. And moreover, our framework allows us to tune these parameters on a more fast way. These plots corresponds to the time of tuning hyperparameters. This blue dot corresponds to the time required for iOpt to solve this problem. And the box plots corresponds to the times for Aptuna and HyperOpt. You can see that iOpt outperforms these frameworks in terms of time. Well, now let me switch to the second part of my talk and come back to the multi-objective and consider my multi-objective optimization problems. Suppose that we have several efficiency criteria. And again, we suppose that all of these criteria can be multi-extremal, black box, and hard to evaluate. Also, we suppose that all of these efficiency criteria satisfies the Lipschitz condition. One way to solve multi-objective optimization problems is based on a scalarization idea. Using some approach, one or another, and using some vector of parameters, we can reduce several criterion, several objective functions into one objective function. This scalarization method, one of this method is presented here, so-called min-max convolution. Again, here is a lambda is a vector of parameters of this convolution. But it's not enough to solve this problem for one vector of parameters lambda. To find the Pareto set, we should solve a series of scalar problems, each of them corresponds to particular value of convolution vector lambda. So we talk now about solving not one problem, but a series of optimization problems. The numerical solving of global optimization problem assumes successive computation of the values of criterions at trial points. And the data obtained as a result of these computations forms the set omega of search information. As a result of scalarization and multi-dimensionality reduction, the set omega can be transformed into the set A that consists of points from the unit interval and the values of reduced function after dimensionality reduction. The information accumulated in this set can be used to find the minimum of the next optimization problem. So suppose that we solve one problem, we get the information in the set omega, and we can use it to solve the next problem. I explain you this idea on one example. Suppose that we have B criteria problems, two criterions F1 and F2. First scalar problem corresponds to the vector lambda 0, 1. So we just minimize the function F2. Here we may see again the level line of the function and the points of a search trial that are required to solve it. The number of trials is 128. After that, we build the next problem that corresponds to next convolution vector. Suppose the problem number 3 with this vector lambda. The number of trials required to solve this is 144, but only 7 trials are new. These trials are indicated here by red points. All other trials, the information from about these trials we can reuse from previously accumulated search information. Then we solve next problem. For example, problem number 15 that corresponds to this convolution vector. The number of trials is more than 900, but only 35 trials are new. Here you may see that global minimum moves from this point to this one, and these new red trials are concentrated near their global minimum point. Problem number 35 with convolution vector 0.7 and 0.3. Again, a lot of points from previously accumulated search information, but only 8 trials are new. And the final state of the search process after solving 50 scalar problems. The last problem corresponds to convolution vector 1, 0. More than 1,400 trials, but this last problem, only 3 trials are new, indicated here by red points. Well, but in any case, the total number of trials are significantly large, and we want to reduce it. There are many approaches how to speed up the solution problems of one scalar problem, but we need to suggest some approach to speed up the solution of a series of problems. Series of problems arising when we solve initial multi-objective problem. Thus, the acceleration of search can be based on application of machine learning techniques. We propose the following approach. Let's solve several scalar problems with different vector lambdas. For example, just 3 problems. Let's construct an approximation of a Pareto set using the information obtained by solving of these 3 problems. After that, let's add some penalty for the deviation from this approximation to the rule of selection of a new trial points. Then we solve next scalar problem that corresponds to next vector lambda I, and we add this information into the set omega, come back to the step number 2, and repeat the process. How we can build this approximation? We can use machine learning techniques. We can use linear or non-linear models, logistic regression, linear SVM, or decision trees, neural networks. In our study, we used rather simple linear model based on logistic regression for the following reasons. This model can be trained very fast. The linear model simplifies the penalty calculation, and it's very simple to set weights for the classes. So this plane, this line or hyperplane, separates the Pareto set and all other dominated points. And we transform the rule of computing the characteristic of a search interval on the following way. This term, the first term, is oriented to finding a global minimum of a current scalar problem, and the second term influences the selection of a subinterval to improve the evaluation of the Pareto set. How we can build this separating hyperplane? For each point from the search information, we assign a class label. 1 if this point belongs to the Pareto set, and 0 if not. And the separating hyperplane can be built using classifier based on logistic regression. Of course, at the initial state of the search, this approximation is bad. But when we accumulate the information, the approximation will be closer and closer to the real Pareto set. And when we build this separating plane, after that, we can calculate the distance from the points, from the dominated and non-dominated points to this separating hyperplane. We can scale these distances and compute the value of the characteristic related to the Pareto set as a sum of these scaled distances. The distances in the left lower corner we consider as positive. The distances at the upper corner we consider as negative. And here, this slide presents the effect of using this separating plane. The number of trials required to solve the problem significantly reduces. Of course, we compare this approach with different other approaches. To do it, we use a well-known quality metrics. The first metric is so-called hypervolume index. This hypervolume index corresponds to the volume of this figure between some reference point and the points from the Pareto set. The larger HV, the better. And we use the distribution uniformity index. du, the less is better. This index corresponds to uniformity of distribution of the points at the Pareto set. The first series of experiments was performed to compare our methods with another well-known algorithms by solving this test problem. You may see that our method, global search algorithm and global search algorithm with separating gives a rather good result, the same or even just a little bit higher HV index and the same or even smaller DU index. And moreover, it requires significantly smaller number of trials in comparison with other methods. In the next series of problems, we use a set of methods from the open source JMetal framework. These methods are presented here. The list of the methods are presented here on this slide. These methods are meta-heuristics. That's why we launch it 10 times and average the results. Also, first experiment, we solve a rather simple B criteria problem. First criteria is linear, but the second one is multi-extremal. And also you may see that our methods gives us large value of HV index with a comparable number of trials with other methods. More complex series, more complex experiments. Again, we use a GQLS generator of multi-extremal functions to build their multi-objective problems. Here we see on this diagram their performance profiles of the methods under comparison. We solve 100 big criteria problems, and these lines corresponds to the average value of HV index related to their average number of trials. The higher is the better. And you may see that the method global search algorithm with a separating plane gives us very good results. This line lies higher than the curves that corresponds to all other methods. And the next example, we solve again 100 four-dimensional big criteria problems, and also the situation is more or less the same. The curve that corresponds to the global search algorithm with a separating plane lies higher. It means that for the same number of trials, we will get more correct approximation of a Pareto set in comparison with their other methods. Well, to finalize my talk, the key points, the main results of the second part. The approach, we suggest the approach to use some machine learning techniques to speed up the methods for solving multi-criteria problems. These results shows that embedding the machine learning into the global search algorithm leads to significant reduction of the number of trials with maintaining close values of HV and DU indexes. Well, of course, in future, we plan to use non-linear approximations of the Pareto set that will better fit the Pareto sets over complex shape. And all of these methods are implemented in the IOPT framework. I showed you the link to the framework as one of the slides. Well, thank you for your kind attention. We have 10 minutes for questions.
Yes, sure. Thank you very much for interesting presentation. Okay, dear colleagues, we have 10 minutes for questions and discussion. Everyone may ask a question, please. Okay, you're welcome.
Yes, thank you very much for very interesting presentation. Actually, I have a dozen of questions because I have a very little, but nevertheless, experience in optimization. My first question is, you have started with approach which use piano space filling.
Yeah.
So my question is it possible to build another function which covers search space not only in discrete points, but in any point?
Well, actually, if we consider Peano curve as a pure mathematic object, this point covers the region at any point. But Peano curve is a limit object and will cover at any point if we take a lot of if we take this curve with a large density. So we can build this curve for predefined accuracy. For example, the researcher, the practitioner, want to solve the problem with accuracy 10 power minus 2 or 10 power minus 3. That's why we can build this curve with this accuracy. We don't need to build it with accuracy 10 power minus 6. It's
Okay.
not, it's enough.
And what about dimensionality? Can you tell us something from practice? 10, 100 or more?
Yeah. The question of dimensionality, it's the most important question in optimization. And in our practice, we have examples when we solve approximately 10 dimensional problems, 100 dimensional problems. If we discuss about black box optimization, when we know only the methods of evaluating the function, I think there is no method to solve this type of problems. We required another suppositions to solve it. For example, we can suppose that the function is convex, the function is unimodal. In this case, we can solve the problem of 100 dimensionality. But in this case, we can solve it approximately with dimensionality 10.
Yes, I have asked this question because when we solve some practical problems, sometimes we can find exact solution using evolutionary algorithms, even we have 1,000 of variables. But at the same time, when we run, for example, direct algorithm, it fails. It means it can converge to any point.
Yeah, sure, of course. If you take large scale problem, it's better to use nature-inspired algorithms. But for problems of this type that I show on the screen, maybe the dimensionality is not very large, but there are a lot of extremes, and each of the extreme point have a very small attraction region. In this case, nature-inspired algorithms failed to solve this problem, like you see here, So the problem, these methods can solve maybe 60% or 80% of the problem, but not 100% of the problems.
Okay.
Even for dimensionality 4, for example.
Actually, I have a lot of questions. So if anybody
Well,
wants to ask
yes,
something else,
you
I will stop here.
Just give chance to somebody else to ask questions. Okay, colleagues, who would like to ask?
My question,
Sure.
Garnov Alexander. Colleagues?
Sure, you may start.
Oh, thank you. About relationship between deterministic and stochastic methods. Is it really 10 variables limit to the deterministic methods?
Of course,
Or
it's
not?
not. Of course, it's not a limit. It's not a limit. It's just the order of the problems, the order of their dimensionality, that we can be sure that the method works correctly. Of course, if we discuss about some other type of deterministic methods, like the methods DC optimization or any other methods that uses another assumptions about the objective function, the number of variables can be the dimensionality can be significantly larger. But if the problem is a clear black box problem with hard to evaluate multi-extremal function, I think their dimensionality is an order of 10.
And what about parallel technology? Maybe Gergel, Statyas? Oh, not?
Parallel, of course, parallelization helps us to solve complex problems. You can see that if we solve the complex problem that requires significant time, the time can be reduced. For example, to solve this problem, the time is 31. I don't remember what is seconds or minutes. Sorry, but if we use 80 parallel processes, the time is just 1.6. Yes, sure, it helps. It's helped to solve more problems of more dimensionality, but it helps us to increase dimensionality maybe from even 10 to 15, 15 to 20, but not from 10 to 100, of course.
Thank you.
Thank you for the question. Somebody else?
Yes, I have also a small question. In the beginning, you said that Bayesian optimization is one of the good ways to solve problems. Are you familiar with the so-called efficient global optimization method?
Igor, yeah, of course.
Yes.
We know these methods, and
did you make a comparison with it?
Actually, yeah, we did, but it's my fault. I don't show you the result of comparisons here. We compare it on this class of the function, GKLS functions. These functions are, let me show you again the picture, the graph. These functions are rather complex for the optimization methods because there are a lot of local extremes, and the global one has only a small attraction region. And efficient global optimization also fails to solve some problems in a large set of these problems. For example, we solve 100 problems or 1,000 problems, and in failed to solve some percent of these problems. Of course, it's just the words. Next time I include the presentation of comparison Igor and global search algorithm.
Okay, I see. I mean, just I also tried Ego and worked quite well. Not always. Sometimes it fails, and it fails really bad. But I think actually there is a problem within the standard Ego, is that the methods that they use inside for searching the optimals is surrogate function. So,
yes, to solve this auxiliary problem inside Ego, it uses some other methods. So it's rather complex approach.
I mean, replacing that method actually boosts the performance of Ego quite significantly. So maybe there is a way to make it better. Okay, thank you.
We have to finalize discussion in spite of our great wish to continue, because we are now near the time of finish this keynote lectures. Again, thank you very much, Professor Barkalov.
Thank you again. Again, I show you the link to the page where you may find the implementation of our methods. Thank you.
Okay, thank you very much. Now, our next presenter, Professor Todor Ganchev from the Technical University of Varna, with key lecture, Intelligent Human-Machine Interaction Towards Adaptation to Momentary Emotion Cognitive State of User. You are welcome.
Thank you very much, Professor Semenkin. Just a second, I need to share my screen. Am I allowed to share? I need a second. I hope now my screen is...
yes, we see your screen.
Yeah, thank you very much. Thank you for inviting me for the plenary talk. I will try to be entertaining you without equations. I know the audience is mathematicians, but please excuse me for not having equations. And I belong to the Technical University of Varna, which is the second largest technological university. Currently, we have about 5,000 students and 150 PhD students. This is much less than years before, when we had 3 times more. I'm the head of Artificial Intelligence Lab, and today we'll briefly introduce what we are doing in my lab and some research and projects that we are currently implementing. Our mission at the Artificial Intelligence Laboratory is to create advanced AI tools, and we are typically research and technology development lab. And we develop applications and services. Some of them I will demonstrate today for the education, for the business, for the industry. And of course, we are teaching. We are about 5 or 6, currently 6 persons, which are teaching staff. And we have PhD students and engineers who are helping for the research and technology development. And of course, we are developing applications for the average citizen, the so-called citizen science that empower them to get involved in the ecological and political aspects of our life. I will start with a few words about the teaching that we have at the Technical University of Varna. My laboratory is responsible for the bachelor degree program on artificial intelligence and cybersecurity, of course, along with other colleagues from the Department of Computer Science and Technology. And we also have master program on artificial intelligence systems and cybersecurity, and PhD degree program on artificial intelligence. And we are also teaching school teachers on artificial intelligence in the school. This is a new specialty in the high school, in the high schools of Bulgaria that started from the past year. They have now artificial intelligence for school boys and girls. And we were awarded by the mayor of Varna with the award, gold medal, for our teaching efforts. What is important, however, and what is the emphasis of my talk, is the scope of research that we carry in the artificial intelligence lab. And of course, we are working on digital signal processing and machine learning methods and their applications to computational bioacoustics. This is the study of sounds of nature, biodiversity studies, and studies of key species that are important for the ecosystem. We work on physiological signal processing, which is related to emotion, stress detection, cognitive load detection. My talk today is in the direction of this research, and biometrics and speech technology, which are nowadays common technology, even commercially available, and even technology that is used every day in our lives. And the topic that combines everything said so far is the human-machine interaction. We built applications with intelligent human-machine interaction that combine different methods of our research. We run a number of projects. Iliad is our flagman. We are the biggest partner in this project. 20 million euros devoted to creating digital twin of the ocean. At the end of my presentation, I will come back to this project because it is one of the use cases that come of our technology developed on the detection of momentary state and so on. Another project that just finished is Clouded. We are training non-engineers from all across Europe on using big data analysis and artificial intelligence and all the other modern technologies. And then we just started, we are associate partner in another project, SMASH, Machine Learning for Science and Humanity, where my team is studying the sounds of dolphins and dolphin communication with the aim in 5 to 10 years to make significant achievements like interspecies communication. So let's focus on the talk for today. I will talk about human-machine interaction and with focus on the adaptation of the momentary emotional and cognitive state of the user with 3 different contexts. In every case, we have a computer user at different environments, either in the office, this could be in the case of personalized education, or it could be computer user in business, IT company, let's say, where we have shared office or open office environment. And this is also typical for the marine traffic control in Varna and many other companies where many people share a large hall. And then we will also see the application of this technology in the context of augmented reality, virtual reality through glasses and computer screens for the ship pilots and captains that actually are exposed to the same problems of human-machine interaction. And why do we need adaptive human-machine interaction? First of all, because we are different. Humans are unique. Each person has own character and traits, and we have different background, and we have different qualities and behaviors, and this has to be considered when we develop specific application, maybe a computer game or educational program or whatever. Every person is unique, and we are able to measure this and adapt. And the current research, the current presentation goes in this direction, adaptation. But what do we adapt? What do we need to adapt? People have different cognitive capacity, different capacity to process information and to resolve problems. And people have different emotional intelligence, the ability to understand the emotions of the others and own emotions and the consequence of interacting with other people. And different people have different stress management skills. To some people, stress helps to some degree. To other people, stress kills their creativity. Everybody, every one of us has different strategy how to manage stress. And then our performance depends extremely on our mental state of mind. It is obvious we are experiencing this every day. Even the same person at two different moments of time behaves differently and has different performance. Is it possible to compensate for the current state of mind and keep performance high? If we are able to do this, it has many applications. For instance, in the human-computer collaboration, it is very important that the efficiency of collaboration remains high for prolonged periods of time. And for example, in the industry, when there is collaboration of people and robots performing operations on the same object, then the mental state of mind of the person could be reason not only for low efficiency, but could be reason also for injuries and some unpleasant situations. And of course, when we are talking about human-machine interaction, there are many other aspects that we need to consider: the focus, the inspiration, and many other human states that are important. So what is common is that we have a human and a computer. And then, as you see in this picture on the left, we have a person sitting in a chair watching a computer screen. And even if the chair is specialized ergonomic chair, and even if the screen and the keyboard are placed properly, we still have some, let's say, adaptation of the human. The human tries to adapt his pose to the working environment, which means that he is not able to stay like that for 8 or 5 hours, or maybe 10 hours per day, depending on the profession. Because if he does so, he will develop some problems with the spine, or maybe with the elbows, or maybe with some other parts, because muscles and bones are under position which is not very, how to say, natural for humans. And this is the typical scenario when the human adapts to the computer, by the means that computer has some algorithmic approach, and then humans try to behave like they are following the algorithm of using computer. Maybe it should be different. Maybe the computer or the system or the machine should be able to adapt to the human and escape or make possible that human does not feel pain or inconvenience while working with a computer. So ergonomy is a very, very important part of human-machine interaction and human-computer interaction. And we study this in a different project. I will not talk about this today too much, but ergonomy is a key for preserving human health and preserving humans from, especially kids, from muscular and skeletal disorders. Some of them are irreversible. And then comes the question, what kind of adaptation shall we aim? Of course, we have the human part that adapts, as we see. We have the machine part that also can be subject to adaptation. And we have the context part, which is also possible to be adapted. What kind of adaptation we need in order that human-machine interaction becomes less dangerous for the human, more pleasant for the human, and more efficient, regardless if it is human robot or human computer or human system interaction. Probably we shall do adaptation in all the three sides, not only adapting the human to the computer. And this is the subject of the project that I will speak today. I will speak about a project called Investigating the Possibilities for Development of Intelligent Human-Machine Interfaces in the Direction of Recognizing Risky Cognitive and Emotional States. It is a project that is funded by the Bulgarian National Science Fund. It started 2019 and will finish in the summer of 2024. And talking about intelligent human-machine interfaces, we shall understand adaptive interfaces, interfaces that in some way adapt to the person, to the task, to the context, or to everything, maybe. And in this project, we have some priorities. Maybe the most important one is to develop conceptual framework of adaptive system that can perform adaptation in various ways. And in order to develop the machine learning models and the adaptation strategies, we need to create resources. These are data sets of recordings of physiological signals. And then we built statistical models and some AI tools, which are needed in order to demonstrate the adaptation and how it works. And today I will show you some brief results from the e-learning scenario. And we talk a little bit about other scenarios. Potential applications of these adaptive human-machine interfaces are many, but more or less we consider here the e-learning scenario and the high-risk professions like risky crew, decision makers in control rooms, and some others. And I will start with a very brief introduction to the conceptual framework that we use in order to create this technology. It is based on the implementation of emotional intelligence in human-machine collaboration systems. There is very old theory of Lars Rasmussen, who presents the skills needed for skills needed for solving different tasks and the level of attention and certainty of these tasks. So this is the inverse pyramid, which shows that on the low workload effort tasks which are very simple, like driving a car or doing things that can be really automized by the human, we solve the problems on the level of skills. We just are able to automate to solve the problem by learning some skills. Other tasks that require medium to high workload, cognitive workload, are rule-based. We need a little bit more attention because the level of certainty is not so high. It is medium level of certainty, but we still can apply some rules and solve these tasks quite efficiently without using the whole capacity of our working memory or our brain power. And then there are tasks which require very high attention, and because they are not well structured or there are no specific rules for solving these tasks, and then we depend heavily on knowledge. We need to concentrate. We have very low certainty how to approach the problem, so we need to give our best to mobilize all the human resources in order to solve the task and to be successful. And this is the skill rule knowledge pyramid that can be really the foundation of human-machine interaction interfaces. The interface should recognize at which level of complexity and workload every human is experiencing, because different people may face different challenges at different moments of time. Imagine new trainee, new young car driver who is just in his first lessons of driving a car. He has not formed efficient skills for maneuvering the car. So for such a person, probably because of his insufficient knowledge and his insufficient understanding on the rules on the road, he will experience very high workload. I remember when I was having my driving lessons, the first time I had terrible headache just for half an hour driving. My head would explode because my skills were not formed yet. I did not fully understand the rules, what I do in the car, how I behave on the road. And this is a task of high complexity at that time, at that moment for me. But then years later, I would say 30 years later, this is a task with low complexity because it is reduced to specific skills and it does not take too much of my brain power anymore. So this parameter also shows not only the attention and certainty when solving a specific task, but it shows something else that depends on the background of the person. And there is a very, very interesting research years ago. I would say this is classics. And this is very popular as Yerkes-Dodson law, which shows how the level of performance of a person, depends on the arousal, on the emotional arousal or the cognitive arousal level of that person. Arousal is indicator first of the level of attention and concentration that the person has, and then we are trying to relate how the performance of that person depends on the arousal level. And the Yerkes-Dodson law says that when arousal is low, then the performance is low, because typically in such situation, the person does not really follow what happens. He is not interested, bored or whatever. With the increasing of the level of arousal, then the performance increases, because the person starts to comprehend better the situation, his attention is improved, and his interest to solve the problem is improved. And then at some point of arousal, we have the optimum value of arousal. That means a person is a little bit stressed. This stress is productive because it helps the person to achieve his best performance for that situation, for that moment. And if we increase the amount of complexity, if we push a little bit more the person and his level of arousal and stress increases, of course, for the stress, it is also important the balance of the emotions, not only the arousal level, but here we show only the arousal, but with more stress, with higher level of arousal, performance of that person drops again, because of the inability of that person to process so much information, or the difficulties that stress induces in that person to process the information. Such problem usually arises in high stress situations. What the Yerkes-Dodson law shows that some stress usually helps every person to overcome obstacles and challenges, but it is different for every person. This curve is different for every person and every situation, and it's very, very important to be able to detect how it goes. And it will be even better if the system could follow the user performance and monitor the arousal and balance and stress level and cognitive load at specific moment, so that the system adapts its parameters in a way that is really keeping the user in the best performance stage. Too much stress kills. Not enough stress means the person is not really interested. So how to do this? How to automate the process of keeping the person at specific level of stress that is really keeping him productive with high performance. In order to solve this, in order to address this problem, we created a database it is available, publicly available through the IEEE data port. And this database is, let's say, designed in a way that we are able to measure the cognitive load of a person with different tasks. Stroop test, which is a very simple exercise that requires very low attention level. Then we have some mental arithmetics tasks. This is elementary arithmetics, but can be considered not very difficult task because these are really things that a person can do without a calculator. And then we have a more difficult test, which is an IQ test that keeps the person busy. And this test has high level of uncertainty, what will happen, so that the person has a high level of attention. And based on the responses of 100 people, I believe in the version of the database that we provide to the people is 60, but we recorded more than 100 people, and these people have specific profiles. Most of them are young people, but not all of them, and some are very efficient at high levels of stress, and others are very inefficient and high level of stress. So some fail, some succeed in these tasks. And then we are able to identify how many people have different level of experience, how they experience different levels of difficulty. And we built models based on which we are able to recognize the cognitive load for every person. And we also capture the emotional state of the person, which is not shown here. And based on the emotional state, we can measure the level of stress. And then we are able to model the level of stress or detect negative emotions and stress level based on physiological signals. And based on this research, we are also able to find the locations of or to split the people to several different profiles. People who are very successful under high concentration, they have high cognitive capacity, or people that are successful with low cognitive capacity or with low workload. These are, unsuccessful, I should say, unsuccessful. And then people who are unsuccessful because of the low concentration. And then we have people who are successful under low concentration. And these are different categories of people that have different behavior and different need of adaptation of the system. And the database was recorded in a very simple setup using specific units for measuring the electrocardiographic signals and surface conductivity of skin. Based on these measurements, we extract a number of parameters related to heart rate variability and other parameters which are very important for detecting stress and emotional conditions. And for the skin conductivity, we also extract a number of parameters which show the level of stress and the level of difficulty, from the perspective that when it is more difficult, conductivity increases. And making some assumptions, we are able to estimate the arousal, attention level, emotional state, valence, stress level, cognitive workload, and the reaction time of every person, which are the physiological parameters describing its current state. We also experimented with commercially available software like the Morphcast platform. They are using cameras, and I would say the cameras are almost as good as the direct measurement of physiological signals. But what is important here is that we are able, based on such components that are able to detect emotional state, arousal, attention level, stress level, with the help of camera, the gaze, where the person is looking at specific moment. I mean, we can even know a specific line in the screen, a specific position the person is looking, what is the level of his attention. And based on such components, we developed the overall architecture of adaptive system that incorporates human-machine interaction. And then we made a decision manager, which shows to the rest of the system if adaptation is needed or not. We have this decision made based on the application, on specific application, based on the user model and the data that come from the sensors, and based on the context. We also model the context in order to make appropriate decision if adaptation is needed. And I will not go too much into details because time is not so much, but the adaptive ability of the system is first on the adaptation of the task, of the application. For instance, we developed a computer game which is adapting the speed so that it keeps specific performance of the gamer, of the user. If we keep the performance between 85 and 95%, that means that we induce some cognitive load, but then the user feels that the game is interesting, and then he would stay longer with the game, unless the game is very difficult and he quits, or the game is very easy and he wins easily. I mean, with such adaptation, with the adaptation of the task, changing the speed of the task, we could engage the user longer. This is universally accessible games. This makes the games interesting to wider community of people. So more people are interested to pay for the next level, because complexity is in the level of interest. We also have adaptation depending on the user input and user profiles. We are profiling users in several categories depending on what I show you in the diagram earlier. We have also a way to adapt the context. Of course, limited adaptation in a smart home environment. This is more easy because we could control the ambient noise, or we could control the illumination, the amount of light that is coming to the specific desk or position of the user. But we have developed this as a concept, and now we are experimenting with the adaptation of the context, because the context is very much related to the cognitive capacity of the user and to his ability to solve problems. Imagine if this is industrial environment where let's say the context needs to be optimal for each user who is working, or for each employee who is working with a robot in collaboration, solving some tasks on the pipeline for let's say assembling cars or assembling washing machines. And then we have the decision manager that combines the different aspects of context of the application and the user and makes decision for making adaptation. And this adaptation could be shown as feedback to the user, suggesting him something or informing him about something, or can also change the environment in a way so that the adaptation brings a better situation. I will not go into detail too much of the workflow, but we have different levels of processing the information that is coming from the user typically has text, audio, video. It has the physiological signals that we make, the gaze tracker with the camera, and some other inputs, everything that the user provides and that is acceptable. We are collecting this information and are extracting some specific features, and then we do interpretation of this information in order to extract the stress level, the degree of attention, cognitive load that the person experienced, or the progress, the actual progress that he makes, and the context conditions. And based on these parameters, then we use specific modules and profiles to make, let's say, information fusion based on the different modalities, and then some decision making if adaptation is needed or not. And then depending on the decision, we can do either task-related adaptation and context-related adaptation. So this time we do not adapt the user, but we adapt the task, or we adapt the context in a way that helps for keeping higher efficiency. And then in order to evaluate if our adaptation is successful and if our adaptive system really works, we collected a second resource, a database that is again freely available through the website of my lab. In this database, which is called Ethics, we collect the timestamp, the stimuli that are provided to the user. This is a very simple computer game where the user is exposed to sequence of digits and letters, and then there are some rules that he has to follow and to press buttons, and then we measure the performance of the person, his speed, the reaction time, and we also are able to control the speed depending on the performance. So we implemented the adaptation that I was describing there in order to make the task adaptation so that we keep the person in specific success rate, so that we control his performance. And then we are currently working on adaptation of the context, providing different adaptation, so that the second mechanism of adaptation is also evaluated, how successful it is. And in the database, we provide high resolution video with audio from the PC camera. Of course, the face expressions captured this time with independent tool, not with our components, but with MorphCast, so that we have a comparison what is going. Let's say we use the not so high performance tool, MorphCast, which measures indirectly through camera as reference to measure or to estimate if our contact direct measurements are aligned or not. This is like independent channel for measuring what is going on. And then we have everything recorded, and we are available to provide this. This database is small, 21 persons only, but I will show you some results. What is interesting is that the Yerkes-Dodson law changes for different complexity of the tasks. And when we have easy task, it is shifted. When we have easy task, it is the whole curve is shifted to the right, and then the optimum level comes at, let's say, higher arousal level. And then when the task is hard, the optimum performance comes at lower stress level. I mean, this is one let's say, indication that stress kills performance when the task is hard. But then if the task is easy, you need higher attention and arousal level to keep for very long periods your productivity. Putting aside the theoretical aspects, I will show you what happened in the e-learning setup. I will not go into detail explaining the way we model and how we develop the computer game. More or less, I consider this not very interesting at this moment, but I will show you directly the results. And this is a plot which shows the cumulative performance of a person against the arousal level. So we have arousal against the performance of each person. And for the different people, you see the plots are quite different. Of course, people are different. We knew this from the very beginning. And that means that people achieve different performance under different arousal levels and different concentration because of their difference in capacity, in attention, motivation. There are many different parameters that we cannot control. And this is why people are so unique. But what will happen if we use adaptation to the specific user based on his initial session? The results are shown here. Based on the initial session of each person, we can develop person-specific module. And then while he is playing the game, we can control the parameters of the game so that they are equally difficult to everybody, so that we keep specific performance level. And on this plot, you see the attention level and the arousal for different people. And we see that the arousal attention is almost the same for everybody, except some group here. Yeah? We decided to investigate who are these people. So based on the questionnaires they filled earlier before the tests, we found out that those people that do not follow the ordinary plot, they probably they do not adapt, or we cannot model them very well to make the adaptation proper, are left-hand users. There were several people left-handed that we need to model separately. The adaptation of the system should be different to those people, because otherwise we cannot achieve the adaptation properly. And at that point, I need to summarize some implications of the research that we are doing. It is very important to monitor human features like attention, emotional state, stress level, cognitive load, and many others, because these are important for the momentary performance of each. And these parameters may vary significantly with time. And the momental state of mind is a critical factor for achieving good performance. This is obvious. I do not need to prove it. And then adaptive e-learning system that is aware of the momentum state of mind will adapt its operation to preserve the optimum level of cognitive load and optimum success rate of that person. And then adaptive system will permit better efficiency of the human-computer interaction. And then there are many applications. Education is just one of them. If you permit a minute or two, I will show you something else that is related. This is the Iliad project I mentioned in the very beginning. We are developing digital twin of Varna Port. It is a huge area. Varna Port is 30 kilometers long and let's say 2 or 3 kilometers wide. And currently, under unfavorable weather conditions, the port remains closed, which means economical difficulties for the industry. So we developed a digital twin of the Varna port, and based on this digital twin, we developed 2 applications. The one is for the traffic control, for the marine traffic control. It is the center here, and we use high resolution of weather prediction in different regions of the port, very high resolution, location-specific ways to predict weather. And based on these predictions, the traffic controllers can really make a responsible decision which part of the port should remain closed, which shall be open. And for the very special case when there is fog, we developed application based on augmented reality and virtual reality for blind navigation. And in the glasses, you see the laboratory setup. In the glasses, person sees all the markers that are important for navigation of the ship. And the blue line is the one that the pilot should follow. This is the same from elevated view. We are able to demonstrate through the glasses various views. At this time, we already have a very high resolution of all the objects that the captain needs in order to navigate the ship through the channels. And you see, beside the glasses, we also use transparent monitors to demonstrate how it works as technology. What is? Sorry, my time is over. Sorry.
It was close to over.
Yeah, just 20 seconds more. So this was demonstrated in a real world that it works. And then you see the captain with the fog, and then after wearing the glasses here below, the fog is removed. And what is black is transparent, so the captain sees through the glasses the environment without. And then here are the traffic controllers in the room. They need to control the traffic in Varna port, and it's very important that we make adaptive interface for them. Thank you very much. Sorry for taking too much time. That was.
It was not too much, but very interesting. I have myself a couple of questions. First of all, what does it mean, negative arousal?
Sorry, could you please? I couldn't hear. Sorry.
Negative arousal. In your
arousal, the emotional arousal. Yeah, it is
negative. What does it mean?
Yeah, the emotional arousal. What does it mean?
Yeah, negative.
Yeah,
negative.
Emotional arousal is the level of excitement that the person feels. The level it is related also to the level of attention, and it was negative at specific plot because it was normalized to be with Gaussian distribution. Okay. So
just enough. Thank you. I understand. And the second question is on the slide number 26. You only left up, there's text and speech. Yes. Text and audio. What is the difference?
Text is from the keyboard, from written text. And then audio is rечевой signal.
Yeah. We just had one project with foreign partners recognizing emotion in speech without any attempt to understand what words mean, just the sound. That is why I asked it. Thank you. Okay, colleagues, any question, please?
Well, may I ask a question?
Yes.
The question is, today we usually use so-called deep learning. It means that we can get some special features from data and use it later in machine learning. And usually these features are not understandable by human. Is there any risk that this artificial intelligence in human-machine interaction will be so complex we will never understand that this artificial intelligence is really useful or maybe not dangerous for us? How do you think?
Thank you. It's a very, very interesting question and very difficult to answer. Of course, there is danger. And this is why in the European Union, now there is this confederation of laboratories that are doing artificial intelligence research, and 4,000 laboratories and several thousand individuals are collaborating on establishing rules how to build technology which is transparent, predictable, which is not biased. It's very easy to develop technology which is biased simply if the data set is not really representative for the for all the cases. And Europe is leading the establishment of rules and standards how to develop AI technology so that we really have low risk of creating a monster. Of course, current neural networks, the deep learning neural networks, create models which are not easily to interpret. But then it is the challenge that we, the researchers, build the components so that we can interpret what is input and output of each component. And then if we have this interpretation, you still do not understand what the black box inside is doing. But if the output is predictable, if the output is reliable, if it fits to some standards, then we reduce the risk of something going wrong, probably. At least we are hopeful. We do not have definite answers.
Yes, thank you. Just an idea. If our ability is so limited, maybe we need to develop artificial intelligence, which will help us to understand another artificial intelligence.
We need to develop more natural intelligence, not so much artificial, probably. Thank you.
Okay, thank you. Dear colleagues, we have more 3 minutes to ask questions, please. No questions. Let me come back to my question about speech and text. Do you have such an ability to recognize emotions by speech?
Based on the voice of a person?
Yeah.
Yeah. This is technology that exists now for 20 years or more. I was working this as a PhD student, and based on the prosody of the speech, you can really recognize the emotional state of the person, and then based on this emotional state, you can really infer if the emotion is positive, negative. Some people are able to recognize the basic emotions, which are 6, and some people pretend they are able to recognize more than that. But it's really difficult because humans use buckets of emotions. Emotions in humans is not just one. At the same time, a person has several, and you usually recognize the dominant one at specific moment.
Yes, that is why I ask. We did it for 4 languages, not human specific, but there is a difference in sound, in emotions. Yeah, we did it for Germans, Americans, Japanese, and Russians, and approximately the same sound can demonstrate quite different emotion if person is German or Russian. That is why I asked.
It is the cultural background, and of course it is person specific, because if somebody is using irony, this is a very complex situation.
Yes, exactly. We demonstrated such a, let me say, if a system will recognize words, what they mean, what does words mean, but and react, it could be absolutely stupid reaction, because person can say very bad words, but it's very specific intonation. It means a joke, for example, something like that. Okay, thank you very much for your presentation. And now we change our speaker. The next speaker is Professor Dimitrios Gerontitis from Thessaloniki University, and with his tutorial, Activation Functions in Zeroing Neural Network Neurodynamics. Okay, thank you very much for your presentation. You are welcome.
Okay. Can you see my screen? It is observable, my screen? Okay.
Yes.
Hi, I am Dimitrios Gerontitis, and I'm going to present you the tutorial with title Activation Functions in ZNN Neurodynamics. But first, let's see some basic things about this area. The main goal of this tutorial is to present the different activation functions applied in the ZNN dynamics and compare their behavior in solving the time-varying Sylvester equation. Where Sylvester equation is given in a Formula 1. So the first step to solve this type of problems is to define the following error matrix function. We must mention that when we want to solve this type of problems in numerical linear algebra problems, a good trick is to vectorize a problem. So we obtain a linear time-varying linear system. After we make this vectorization, the next step is to define a ZNN dynamical system which enables convergence of e to t to the zero vector by the dynamics given in equation 4. Equation 4 describes a known Young neural network where the F is denotes an element-wise vector mapping on each e to t by an appropriate monotonically increasing a node activation function g, and the parameter gamma is a positive real number which increasing values accelerates the convergence speed of the non-linear ZNN formula 4. Now, in this slide, I present you the Simulink implementation of the ZNN formula 5 for solving the time-varying Sylvester equation problem. We must mention that a good tool for the solution this time of problems is to design the Young neural network or another recurrent neural network in the Simulink. Simulink is a specific environment of MATLAB's software. Different types of AFs generally lead to different convergence properties. It's really good to mention that the good activation function enables a finite time or sometimes predefined time convergence probability for any positive constant gamma. So when we want to study this type of problem, the first step, except the error function, is to considering the Lyapunov candidate for each element of the error vector e to t. And then take the derivative of the Lyapunov candidate, and we have the relationship 6. We can see that the derivative of the Lyapunov candidate is 0 when the element of the error vector is 0, and negative definite when each element of the error vector is different than 0. This property, according to the Lyapunov stability theory, implies the global convergence of each element of the error vector to 0, which is the initial goal. Now, in this step of the presentation, it's really useful to mention the lemma, this lemma, which says that assume that when we have a continuous positive definite function, which fulfills the inequality 7, then we have the inequality 8, and the Lyapunov candidate is 0 after time t, where t is equal this. We must mention that when we use the finite analysis, the convergence time, it depends from the initial condition of the Lyapunov candidate. Now, this lemma describes the predefinite analysis of the ZNN model. If we have parameters C1 and C2 which are positive, the parameter P is between 0 and 1, and the parameter W is larger than 1, such that inequality 11 holds, then the Lyapunov candidate is 0 for any parameter T larger than convergence time T, where convergence time T in this case is computing by this formula. So we have mentioned the finite analysis of a dynamical system and the predefinite analysis of the dynamical system. These inequalities 7 and 11 are useful because when you want to build a new activation functions, your main goal is to have these inequalities which will decrease the convergence time. This is the main goal when you design new models or new activation functions. But two common requirements assumed definition of arbitrary AF is that it is monotonically increasing in order. Some of them are the linear activation function, the bipolar sigmoid activation function, the power sigmoid activation function, the smooth power sigmoid activation function, the power sum activation function, and the hyperbolic sine activation function, wherein is a not integer. Some other, which includes finite analysis, are the sine function, the sine by power function, or the no or as Lie function from Professor Swiley, the tunnable activation function, the versatile activation function, the extended versatile activation function, order n, where the parameters pk are between 0 and 1. All the parameters of the set WRE are larger than 1. A1, A2, A3, A4 satisfy the same constraints as in previous VAF activation function. The parameter A5 is 0, A is larger to or equal to 0. And the parameters are satisfied at this condition. I mean that we take the set of PK and WK with increasing property, increasing values. From the relationships and by definition of Lie activation function, we obtain this about this relationship about the Lyapunov candidate. So when we have this equation, the next step is to take some cases about the elements of the error vector E of t. The first is that if sum of elements are equal to 0, then it is observable of the definition of the Lyapunov candidate, or the derivative of the Lyapunov candidate is 0. Here, if A of t is 0, then all this is 0. The equation 44 is 0. When we have some elements equal to larger than 0, positive, then it is observable that we obtain the inequality 25. So we have, when the sum of the elements of the error vector is 0, then the derivative of Lyapunov is 0. When some of the elements are positive, we have inequality 25. And when some of the elements of the error vector are negative, then with the same method, with the same way, we obtain the inequality 25. So we can use because the properties of lemma, the first lemma, are satisfied, we can take the application of the first lemma, and we have the convergence time for the Lie activation function. With the same way, we can do the same way for the versatile activation function. So from 6, and by definition of versatile activation function, we obtain the equation 27. In this step of the proof, following cases about E of t are considered as in Lie activation function. We take the same cases if the elements are 0, positive, negative. So with the same method, with the same way, we have the inequality in 28. So we stop here and we think, okay, we have the inequality. So we have the properties of the second lemma, and then it is observable that we can apply the results from the second lemma. So with application of the second lemma, the estimation of the predefined convergence time from Zien and Vogel activated by versatile activation function is equal with this formula. So we notice that when we use this convergence results for the dynamical systems in first lemma and second lemma, we can compute different convergence times for the Zien model activated by different activation functions with this way. So it is more clear that we can use these techniques to construct our activation functions, so which will make the convergence time smaller. And this is a main goal and an important goal for the researchers who wants to make research in this domain. Now, let's see some numerical experiment. It is interesting to apply the AFs mentioned previously for the ZNN dynamics for solving the time Horace Sylvester equation. So we consider these following coefficients, where theoretical solution is given by V star E of t. Now, we clear here that we can use this. From this figure, it is observable that we have the error behavior. Because, you know, we use the error behavior to see that if our model with our activation function converges faster to 0. From this figure, we can see that the error of the time variance Sylvester equation converges faster to 0 by using the FF order 2. It converges to 0 in shorter time instance than tunnable versatile activation function and Lie activation function. Furthermore, we can see that the first figure, we have the parameter gamma equal to 1, while in the second figure, the gamma parameter is equal to 10. Another result we can observe is that as the parameter gamma increases, then we have faster convergence property. This is an important advantage in the ZNN dynamics area. From this now we can see the norm behavior of the error of the time variance Sylvester equation, comparison with FF order 2 between activation and against hyperbolic sine activation function 18 when m is equal 1, 3, and 5. we can see, and in this case, that the FF order 2 converges to 0 in shorter time instant. So it is observable that the ZNN dynamics activated by FF order 2 includes faster convergence property than hyperbolic sign activation function 18. Furthermore, we strengthen the fact that as parameter gamma increases, then we have faster convergence property. Now, in this figure, we make the comparison between activation function FF order 2 and the power sigmoid 15 and power sum activation function 17 for parameter gamma 1 and 10. And in this case, for this comparison, we can see that the activation function FF order 2 includes faster convergence ability against the power sigmoid and the power sum activation function. So from the previous feature and this feature, we can see that first, the activation function FF order 2 includes faster convergence property. And a good way to measure which activation function is the best is to measure the error of the time varying Sylvester equation formula. So we can see from this that because of this error converges faster to 0 with activation FF order 2, that a good reason is to use this activation function for the solution of the time varying Sylvester equation problem or different numerical linear algebra problems. In this presentation for this tutorial, we use the Sylvester equation. We can see the elements of VD produced by a FF order 2 activation function for gamma equal to 1 and 10. Here, the black dashed line is the theoretical solution V star of T, we mentioned previously, of the time varying Sylvester equation 1. And the red lines continuous are the lines produced from our ZNN model activated by this activation function. It is observable that the theoretical solution and the solution produced from our model are in agreement. And as parameter gamma increases, we can observe that we have excellent agreement between our solution from our model and the theoretical solution. So we can see, we all have as already mentioned, we can see that the order 2 extended versatile activation function indicates faster convergence ability against previous AFs. The red lines of the ZNN dynamics activated by our FF order 2 activation function converges to the theoretical solution V star of T. And this experiment shows the applicability of activation functions in the ZNN formula for finding the solution of the TVCA 1. Now, let's see some conclusion. Here in this presentation of the tutorial, we the basic activation function applied in the ZNN dynamics are presented for the solution of the time varying Sylvester equation. This tutorial investigates the influence of AFs on the convergence time of underlying ZNN formula 4. Furthermore, a numerical experiment performed by the Simulus C group strengthens the fact that the non-linear ZNN dynamics activated by different activation functions can be used in problems which needs the solution of time varying problems. So, okay, we can do the same for the Lyapunov equations, matrix inversion problem, and other time varying activation, other time varying matrix equation. Now, okay, we see that we have some specific activation functions. The property which includes these activation functions is that are odd and decreasing. So, a good challenge is, can we have convergence when an activation function is neither increasing? One example is this activation function g of x described in equation 29, where includes the properties of an activation function, but they are neither increasing, neither odd. So it is a good challenge to see. We have analysis. Can we use this type of activation function in the non-CNN dynamics for the solution of more general time-variant problems like Riccati, Young-Baxter, not the traditional linear matrix equations? This will be a good challenge for research. Thank you.
Okay, thank you very much for your tutorial. Dear colleagues, any question, please?
We have time of questions, asking whatever you want.
Yeah.
It was a tutorial because, you know, when for a researcher, what goal wants to have to make better activation functions with faster convergence stability. It was a typical, it was not. It was a basic tutorial, a basic tutorial.
Okay, I have a question.
Yes,
Can you
please.
tell us in short, please, such thing? Many people who deal with machine learning, when hear something about neural networks, usually think about regression, classification problems, or maybe about computer vision. Why this approach is also called neural network? It's rather different from what we usually talk about neural networks. Can you explain in short why we can also say here neural network?
Okay, it is a good question, and thank you for this question. It is not a typical neural network because, you know, you have used in artificial intelligence some artificial neural networks, and I understand your meaning. But let me share my screen again. Just a minute. Oh, nice. Can you see this Simulink model? It's a dynamical system, and because of this integrator, we make some loops, we make some recurrences, as I can tell. So because of this scheme, this feature, and because of the behavior of the dynamical system file, we can call it a recurrent neural network. Okay, it's not a traditional neural. This category, it's not a traditional neural network. It's a recurrent neural network. It's the behavior. It's more of dynamical system and system of differential equations. But because we make these loops, we can say that it is a recurrent neural network, and we can use it except for the solution of time-variant problems. It can be applied in different robotic problems, which will need to compute the trajectory of our system. Because, you know, when you want to compute the trajectory, you want the behavior of your model and the behavior of the trajectory robotics you study to be near. So we can define an error function and apply the RNN model. But because the basis is that because we can design this in Simulink, the behavior, we can understand that the behavior is to call a recurrent neural networks, not a typical neural network, but it's a recurrent neural network.
Okay, thank you. And next question, based on this answer, many recurrent neural networks are used for different problems with text understanding or image processing. Is it possible to apply zero neural networks in such applications? Maybe not now, but in future.
Yes, because you know, except the traditional robotic application, I have make some application in data science, some DNA computing application. Because, you know, sometimes when you want to compute a DNA sequence, for example, maybe you will need the computation of a pseudo-inverse of a matrix. So you can apply the CNN model, make the computation of the Moore-Penrose inverse, and you can compute then whatever you want. The basic is that if you have any problem, you can obtain a linear system or a time-variant matrix equation. You can apply the RNN formula.
Yes, very interesting because, for example, ChatGPT use recurrent neural networks, but it's a very huge, large model. if we can express it using some matrices and operation of inversing these matrices, maybe ChatGPT become very small and very efficient, and you can use it even on your smartphone.
Yes, I agree with this observation, Professor.
Yeah, thank you very much.
Any more questions? Okay, no questions. Thank you very much